Okay, so we've looked at constructing volumes by taking cross sections, and so long as the solids are solids of revolution, taking cross sections in one or the other direction will result in an annulus. Since the area of an annulus is known, we can then add up the volumes of all of those annuli, and that gives us the whole volume. Now let's look at an example where the washer method isn't going to work all that well. It will work, technically speaking, in the sense that the cross sections will be annuli, but we're going to end up with, well, we're not going to be able to write down the integral quite as easily. So find the volume of the solid obtained by rotating the region bounded by this curve and the x-axis about the y-axis. So let's see what this looks like. So the curve is 2x squared minus x cubed. Like so. And we are looking at the region that is bounded by this curve and the x-axis. So that means we are interested in this region. So let me isolate the region of interest. Looks like it's only going from 0 to 2. And then we are going to rotate this about the y-axis. So bring up the 3D view. Rotate this about the y-axis. Oh my goodness. Oh, whoops. I'm sorry. Not F, G. Because G is what we're calling the bit that we're interested in. And let's also put in a segment to make the bottom. So that's going to be a segment connecting the origin to 2, 0. There we go. So we get this sort of bundt cake looking shape. Now, if we want to find the volume of this, should we take vertical or horizontal cross sections? Well, seems pretty clear to me that horizontal cross sections are going to do it. Now here's the problem. If we take horizontal cross sections, we're going to have to write this, we're going to have to take this function and rewrite it so that it's x equals a function of y, as opposed to y equals a function of x, right? We're going to have to solve this equation for x. How do you do that? I mean, I don't know how to do that. We need to solve the equation y equals 2x squared minus x cubed for x. That's really easier said than done. In fact, I'm not convinced that you can even do it in a non-trivial way. To be fair, I know that you can do it. I have seen formulas that allow you to solve general cubic equations, so I know it's possible, but it's extremely ugly. So, suffice to say, we're not going to be able to deal with the washer method here. And of course, you might say, well, then just take vertical cross-sections instead. If you take vertical cross-sections, then the variable is x, so there's no problem, right? Well, yeah, except that vertical cross-sections aren't going to give us what we want. They're certainly not going to give us annuli. So it's... yeah. So the washer method just straight up isn't working here, because it requires us to solve this equation for x, but that's easier said than done. So we need another strategy. Well, if taking horizontal cross-sections is a problem, then why don't we take vertical cross-sections instead? I know that I just said that that's not going to work. But maybe I should be more precise. It's not going to give us washers if we take vertical cross sections, right? If we just slice this shape vertically, then we're not going to be getting washers. We're going to get some other weird shape. How about this, though? Instead of slicing this thing vertically, let's see what happens when we take this two-dimensional region, slice that vertically, and then take those slices and rotate them around the y-axis. And there's precedent for this idea, because we know that if we take these horizontal slices and rotate those around the y-axis, we end up with our washers. So it stands to reason that if we take vertical slices instead, and then rotate those, maybe we'll get a shape whose volume we can compute. And indeed, that's what ends up happening. So, let's take vertical slices of this guy and rotate those around and see what sort of shape we end up getting. So, if we're taking vertical slices, then we are looking at values of x. Values of x range between 0 and 2. So the slices are going to be composed of line segments connecting the point s, 0 to s, g of s, like so. Now let's see what happens when we rotate this dude about the y-axis. What sort of shape are we going to get? It's not going to be a washer, but we might still end up with something that we can work with. Whoops. So we get a part of a cylinder. Namely, it is a large cylinder with a smaller cylinder punched out of it, so that we end up with just a cylindrical shell. And indeed, that's what this shape is called. It's called a cylindrical shell. It's a large cylinder with most of its interior removed. But, basically speaking, it's the same as an annulus, only in extended along a different dimension. A big cylinder with most of it cut out. And you can see that as the slices range from x equals 0 to x equals 2, the cylinders that we get are going to fill up the entire volume. Right? Let me turn this back on. If I turn the volume back on, you can sort of see with the transparency, but these cylindrical shells really are going to fill up the entire volume. So, if we can figure out what the volume of a cylindrical shell is, and then integrate up the volumes of all of those shells, it's reasonable to suspect that we're going to end up with the volume of the shape that we wanted in the first place. And indeed, that is the basis of the shell method, in contrast to the washer method, where we're adding up the volumes of little washers. In the shell method, we're adding up the volumes of little shells. So, what is the volume of a cylindrical shell? Well, as I said, it is a cylinder with another cylinder cut out from the inside. So it's the volume of a big cylinder minus the volume of a smaller cylinder. So I've written that out right here. So let's suppose that the radius of the external cylinder is r plus dr, and the radius of the internal cylinder is r. So, so the radius of the internal cylinder is r, radius of the external cylinder is r plus some tiny little bit. So this infinitesimal dr is going to be the thickness of the shell. Let's say that the height of the cylinder is h. Then, the volume of the cylinder is... so actually, let me put a little bit more detail here. So remember, the volume of a cylinder is the area of the base times height. So the volume of the large cylinder is pi radius squared, right, because its base is a circle. So pi radius squared times height. The volume of the internal cylinder is, again, pi radius squared times height. Then all I do to get from here to here is I factor out the pi and I factor out the h. Now, take r plus dr squared, FOIL it, to get r squared plus 2rdr plus dr squared. R squared and minus r squared cancel each other. So the volume of a cylindrical shell is pi times 2rdr plus dr squared times h, where again, dr, strictly speaking, it's a formal symbol. It's not actually a number, but we are imagining that it represents some very, very small but non-zero quantity, namely the thickness of the shell. Now, what I'm about to say isn't strictly rigorous. It's not a perfectly mathematical argument, but it captures the core of the real argument. Now, we are imagining that dr, being an infinitesimal, is an arbitrarily small but non-zero quantity, the thickness of a slice. Now, if we were to actually try to do all of these measurements by hand, we would find that there is a smallest possible length that we can measure, right? If you're using a micrometer, for instance, to measure the thickness of the shell, you will find that there is a smallest possible thickness that you can measure, and you can't measure anything below that. Like, for instance, if you had a handheld micrometer, you can't measure the thickness of an atom. Now, dr is as small as we want it to be. It's arbitrarily small. So let's just assume that dr is the smallest amount that we can possibly measure. What then is its square? Well, what happens when you square a really small number? 1/2 squared is 1/4, smaller. 1/4 squared is 1/16, smaller. 1/16 squared is 1/256, much smaller. If you take a small number and square it, it gets even smaller. So if dr is as small as we can possibly measure, then dr squared is going to be vastly smaller, so smaller that we can't possibly measure it. So we have no choice but to say that dr squared is 0, right? We have no choice. We can't possibly measure it, so either we assign it an arbitrary value, or we just say it's 0. Well, that's what we're going to do here. Therefore, the volume of a cylindrical shell, take this dr squared and just set it equal to 0. So what do we end up with? This dude. So the volume of a cylindrical shell is 2 pi times the shell's radius times the shell's height times the shell's thickness. And this is what I've already mentioned. So if we take a slice of the planar region being rotated, the thickness of the slice is the same as the thickness of the shell. Therefore, instead of writing dr here, we can write dx just as easily, right? Because the slices of the two-dimensional region, right? The slices of the two-dimensional region are along the x-axis. So this slice, the thickness of this slice is the same as the thickness of the shell. So dr is in fact the same as dx. So to get the full volume then, all we need to do is add up, integrate, the volumes of all of these little shells. And that's what we get. So integrating all of this up, 2 pi is a constant, so we can just pull it out front. The radius and height of the shells, well, that depends on where you take the slice, so those have to be functions of x. And then the thickness of the slice is the same as the thickness of the shell is the same as the thickness of the slice. So that becomes dx. And of course, there's no reason that this is restricted to vertical slices. We could do the same sort of analysis taking horizontal slices as well, in which case everything would be in terms of y, right? So same situation where if you take vertical slices, the variable of integration has to be x. If you take horizontal slices, the variable of integration has to be y. Now, yeah, this formula is correct. It is correct, even though my logic of taking dr squared and setting it equal to 0 is kind of based on an appeal to intuition. It's not strictly correct. If you wanted to prove this formula for real, you would have to use integration by parts, which is a technique that we don't know how to do yet. Or, at the very least, I haven't discussed yet. But, I mean, I think that my method here makes a lot more sense intuitively. This is the way that a physicist would talk about it, even if it's not really mathematically rigorous. So, in the previous section, the principal challenge was figuring out the functions big R and little r. Now, the challenge is to figure out the functions little r and h, so the radius and the height of the cylinders. So I summarized some information here. In some sense, though, I think the shell method is actually easier than the washer method, because, as you'll see when we start doing examples, the radius of the shell is always going to be of this form, where alpha is the comes from the axis of rotation. It's always going to be either this or this, whichever one ends up being positive, because this is a radius, so that it has to be a positive distance. And the height of the slice is always going to be the difference between two curves. So I think it actually is much easier to do the shell method, provided it's appropriate. The other thing I want to point out is that if the axis of rotation is vertical, then the variable of integration ends up being x. If the axis of rotation is horizontal, then the variable of integration ends up being y. And this is in contrast with the washer method, where it was the other way around. Okay, so 4 examples. Find the volume of the solid obtained. Oh, I'm sorry. God. Let me say that again. So the radius is always going to look like this, where alpha comes from the axis of rotation. The height is always going to be the difference of two functions. I'm sorry about that. Yeah, so just follow along in the notes. Just follow along in the notes. I'm sorry. This is a horribly unprofessional situation. But I don't want to redo the entire video, so let's just keep moving. Okay, so find the volume of the solid obtained by rotating about the y-axis, the region bounded by this. Okay, so it's the same example that we've been talking about, but now we can use the shell method to do it justice. So what we really need is we just need the radius and the height of the shell. So let's see. What is the radius of a shell? Well, it's the distance from the axis of rotation over to the slice. So the distance from the axis of rotation over to the slice. Well, this slice is at x, right? Where x is any value between 0 and 2. So what's the distance from 0 to x? That's x. That is literally x. So the radius of this shell is just x. What about the height? Well, the height of the shell, as you can see, is the length of the slice itself. So what's the length of the slice? Well, it's the distance from the y-axis up to the curve. And the curve is 2x squared minus x cubed, right? So that means this distance is literally 2x squared minus x cubed. Easy. So as I was saying, the radius and the height are always going to end up being in these forms. So in this case, the axis of rotation is vertical. It's at x equals 0. So that means the radius is either negative x or positive x. Well, negative x is not positive, so it has to be this. So x minus 0. As for the height, that's always going to be the difference between two functions. In this case, it's the function we were given, and the function on the bottom, which was just the constant line at 0. So the height was the function minus 0. So this is in agreement. with what I've already said. But of course you can see it geometrically, as you should. Okay, so now that we have R and H, all we need to do is fill out the formula. Variable of integration is x. We've already seen that it goes between 0 and 2. And then it's just R times H. So x times 2x squared minus x cubed. Don't forget that when it's the shell method, then it has to be 2 pi, whereas the washer method is 1 pi. So let's go ahead and distribute that x. Now we can just hit this with the power rule. So it really is remarkable how a problem which was untenable using the washer method becomes really easy once you move on to the shell method. Let's see. So 2 over 4 x to the power 4. And 2 over 4 is the same as 1/2. So let's just do that instead. And then x to the power 4, a power rule makes that x to the 5 over 5. Now evaluate this between 0 and 2. Let's see, you plug in 0, nothing happens. So all we need to do is plug in 2. Let's see, 2 to the power 4 is 16. 2 to the power 5 is 32. 16 over 2 is the same as 8. So what do we have here? So common denominator is 5. 5 times 8 is 40. 40 minus 32 is 8. 8 times 2 is 16. And then let me just put the pi here, because I think it looks better. Cool. So 16 pi over 5. Not too hard. Once you have the formula written down, these examples are really straightforward. Okay, next. Find the volume of the solid obtained by rotating about the y-axis the region between y equals x and y equals x squared. Okay, so let's move on. Let's move over to GeoGebra and take a look at what this region is. So let's get a fresh slate. So the region between x squared and x, and we rotate about the y-axis. So let's do our standard cleaning up. So these only range from x equals 0 to x equals 1. So let's just isolate those bits. Now we have to rotate it about the y-axis. I think... No, we didn't do this example exactly in the last section, but we have seen this region before. So let's get our angle slider ready. Surface, so H and P. So we get this dude. So, yeah, this sort of bowl shape. Okay, now we are not doing the washer method, we are doing the shell method. So, what was I saying earlier? If you're doing the shell method, if the axis of rotation is vertical, then variable of integration is x, so we take vertical slices. If the axis of rotation is horizontal, then we take horizontal slices, right? The slices have to be parallel to the axis of rotation. Now in this case, the axis of rotation is the y-axis, so that means we need to take vertical slices. So let's see what vertical slices look like. Yeah, so the variable of integration is going to be x, X ranges between 0 and 1. And they have to go between H and P. Like so. So there's our slices, vertical slices. And then if we rotate those around, we should get the shells that we expect. Turn these off. And indeed, we get cylindrical shells. So these are, so we're adding up the volumes of all of these little dudes. That gives us the volume of the whole thing. Okay, so we need to know what the radius and the height are. So what is the radius? The radius is the distance between the axis of rotation and the slice. So from axis of rotation to slice, well, that's literally just x, right? Because the position of the slice is the same as the position of the slice can be at any x value between 0 and 1. So that means this distance is just x, so that's the radius. As for the height is the length of the slice itself, so that is the distance between these two curves. So that is literally top minus bottom. So the top is the line x, the bottom is the parabola x squared. So the height is x minus x squared. Which is what I've written here. So the radius is x, the height is x minus x squared. And again, this is in agreement with what I was writing up here. So the radius is going to be one of these. In this case, again, the axis of rotation is x equals 0. So it's either negative x or x. So it has to be x because it has to be positive. And then the height is just the difference between two curves. So namely, top minus bottom. So x was ranging between 0 and 1, so that's the lower and upper limits of the integration. And then it's r, which is x, times h, which is x minus x squared. Yeah, another reason that I think the shell method is actually more useful in a lot of cases is because in the washer method, you have to take big R squared and little r squared, and taking the square of some big quantity can get really ugly. In this case, you don't really need to do that. I mean, of course, it still could. You still can come up with examples that are arbitrarily ugly, but well. So do the power rule. Evaluate between 0 and 1. If you plug in 0, nothing happens. If you plug in 1, you get 1/3 minus 1/4. So let's see. 3 and 4, common denominator is 12. Don't forget this 2 pi. Common denominator is 12. 4 minus 3 is the same as 1. 1 times 2 is 2. 2 divided, so I'll get rid of that. 2 divided by 12 is the same as 1 over 6. So pi over 6. So there we go. It's pi over 6 is our answer. Very cool. I like doing math in this format. This is actually way, way more fun for me than doing it on the whiteboard would be. I hope that you can follow along, but you know, you can sort of see me doing the arithmetic in my head as we go along. And because you can keep track of what you're doing in real time, it's actually not too bad. Okay, next. Find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals root x from 0 to 1. Okay? So let's get a fresh slate. Whoops. So y equals root x from 0 to 1. Like so. Let's put a line segment here to sort of cut it off. So that's going to connect 1, 0 and 1, 1. And we are rotating this about the x-axis. So get our 3D graphics out, make our slider. I really hope that you can do this on your own in GeoGebra. I think this is just a wonderful, wonderful tool for visualizing things, especially in 3D, because like I can't draw in 3D, so I certainly can't draw in 3D. I would never ask anyone else to draw in 3D either. So I think this does a really good job at showing you exactly what it is we're working with. About the x-axis. We have seen this shape as well, I believe, in the previous section. The difference now... Okay, yeah. So you could totally do this by taking cross-sections, right? You would end up getting annuli. Yeah, we actually did this example in the last section. So what's interesting is that in the previous section we used the washer method to do it, but the shell method is actually going to work just as well. I don't know if it's going to be better or worse, but you know, it just goes to show that sometimes you can do either of the methods. You know, sometimes one of the methods is preferred, sometimes it's not. Now, if we are doing the shell method, then our slices have to be parallel to the axis of rotation. So that means the slices have to be horizontal. That means the variable has to be y. Variable of integration has to be y. That means we're going to have to solve this equation so that instead of y equals root x, we're going to need x equals y squared. Yes. So variable of integration is y. So y ranges between 0 and 1. Let's see. So we're going from 1 comma s, so that's going to be on the line segment, over to s squared comma s, right? Because variable of integration is y means we need to solve this equation. So x equals y squared. That gives us our slices. And then, if we rotate this slice, we should get our shells. And there you go. So there are our shells. So we need the radius and the height of the shells. So what is the radius? The radius is the distance from the x-axis to the slice. So in other words, it's y. It's literally y. So little r is equal to y. As for the height of the shell is the length of a slice. So what is the length of a slice? Well, it's going to be the difference between these two curves. So it's going to be 1 minus y squared. Remembering, of course, that everything has to be written in terms of y here. And that's exactly what I have. Yep. So y and 1 minus y squared. So r times h. So not much to say about this bit. This is all just rote computation with the power rule. I enjoy it though, I'm having fun. I know this must be horribly, horribly boring, but if it's boring and you understand, then it's good. If it's boring and you don't understand, well then we've got a problem. And, you should come to our class sessions so that we can talk about it. Oops. Okay, so let's see. Common denominator is 4. 2 minus 1. So that's 1. 1 times 2 is 2. 2 over 4 is 1/2. And then just put the pi. Just put the pi on top. So pi over 2, which is in agreement. I seem to recall that we ended up getting pi over 2 last time as well. Yeah. Yeah. The next example is pi over 2 also. I don't know what it is about these problems that pi over 2 shows up so often. They probably just picked them so that the arithmetic was fairly simple. Anyway. Find the volume of the solid obtained by rotating the region bounded by x minus x squared and y equals 0, the x-axis, and rotate that region about the line x equals 2. So we're rotating that around a vertical line. Okay. So we had x minus x squared, and so the region is bounded by x minus x squared on the top and the x-axis on bottom. So let me just make a line segment to denote the bottom of the curve. So we are only interested in values of x between 0 and 1, apparently. So there we go. And we are rotating this around the line x equals 2. Oh, I've done it again. I've done it again. Ugh, I'll get better. I'll get better at doing this as the semester goes on, I promise. Maybe. I'll try to get better. I can promise that much. In any case, we've done enough working with GeoGebra by now that this part should be rote. So let's rotate. So put in our slider, 0 to 2 pi. They're being called G and H. And let's see, so GeoGebra has called the vertical line EQ1. So we're going to have to put that in the surface command. And there we go. That's the shape that we get. A flat donut. Or this actually looks like one of the Here's a weird pull. This looks like one of those little rings that you would shoot out of a gun. Maybe this is just me being a 90s kid, but I remember there was these little plastic guns that would shoot these little like foam rings out of them. For some reason, that's what this reminded me of. Anyway. Now we're going to be using the shell method. So in the shell method, we need to take slices that are parallel to the axis of rotation. So axis of rotation is vertical, so that means our slices have to be vertical. And variable is going to be x, correspondingly. So thankfully, we don't have to rewrite anything if the variable is going to be x. Sorry, so I have to make a new slider. So x ranges from 0 to 1. It's just a coincidence that we keep getting 0 to 1, by the way. That's just because these problems were written to be fairly simple. Obviously, in your homework, it might not be that easy. You know, it might be -1 to 3 or whatever. But so connect is s comma 0 to s comma... the parabola is at h. H is what they're calling it. So there's our slices. And there's our cylinders. This is really great. You know, I've never used GeoGebra to such an extent before. It's really thrilling to me just how easy this is. And you can see how the cylinders correspond one-to-one with the slices. This is why I say that it's not strictly necessary that you actually take the full three-dimensional picture. Really, all you need is the two-dimensional picture, because these slices correspond exactly to the approximating shells. So really, the two-dimensional sketch is all that you need. Anyway, so we need the radius and the height of the shell. So let's see. The radius of the shell is the distance from the axis of rotation to the slice. So let us see. The axis of rotation is over here at 2. So the distance from 2 to the slice is 2 minus this chunk. Well, what is this chunk? Well, this chunk is literally just the distance from 0 to the slice, which is x, right? I mean, the slice is placed at x, by definition. So the radius is 2 minus x. 2 minus x. So that we end up getting this chunk here. As for the height, well, the height is easy. That's just the length of the slice itself. So that's the top minus the bottom. So that's whatever this is, x minus x squared minus 0. And that's what I've written here. So the radius is 2 minus x. The height is top minus bottom. So top x minus x squared minus bottom 0. So didn't even write anything. It is awfully convenient that they all end up being 0 to 1, though, I'll tell you that. Convenient for me. So r, 2 minus x, times h, which is that. So again, you have to be careful with the multiplication, because we're going to be foiling here. So 2x minus 2x squared minus x squared plus x cubed. We can clean this up a little bit more, I think. Yeah. Because minus 2x squared minus x squared becomes minus 3x squared. Nothing else we can do, though. Okie dokie, so antiderivative of 2x is x squared. Antiderivative of 3x squared is x cubed, right? Because you get x cubed over 3, but then the 3 and the 3 cancel. And then here we get x to the 4th over 4. Evaluate between 0 and 1. If you plug in 0, nothing happens. If you plug in 1, we get 1 minus 1 plus 1/4. Talk about convenient. 1 minus 1 is nothing. So we just get 2 pi over 4, which is pi over 2 again. Convenience. Okay, so finally, I want to end with just some general observations about the washer and shell methods. In both cases, I maintain that all that you really need in terms of a visual aid is the two-dimensional drawing. You don't need the full three-dimensional drawing. All of the information necessary is contained in the two-dimensional sketch of the region. Now, once you have a picture of that region, you're going to slice it into either vertical or horizontal slices, so approximately rectangles. Now, if you choose to make the slices perpendicular to the axis of rotation, then you will use the washer method. If you choose to make the slices parallel to the axis of rotation, then you will use the shell method. It is your choice if you want, which of the two slices you want to do. if it would look better vertical or if it would look better horizontal. Ultimately, that's up to you. I mean, unless the problem is like asking you to construct the integral associated with the shell method or something. Like, pay attention to what the question is actually asking you, but, in the grand scheme of things, obviously, you have the choice of how you want to slice the region. And if those slices are perpendicular to the axis of rotation, that's washer. If the slices are parallel to the axis of rotation, that's shell. That is the core difference between the two methods geometrically. Now, independent of whether you're using the washer or the shell method, if the slices are vertical, then that means the variable of integration has to be x. So you would have to write the equations that you've been given to be in the form y equals f of x. If you choose the slices to be horizontal, again, independently of what method you're using, if the slices are horizontal, then the variable of integration has to be y. In which case, you would have to write all of your equations to be of the form x equals f of y. Now, which of the two methods is actually more useful ultimately varies based on the problem. The rule of thumb that I go by is I want to avoid rewriting the equations that I've been given, if that's at all possible. So I'm going to choose whichever method allows me to avoid rewriting the equations, right? So say, for instance, that I've been given equations in the form y equals f of x. I think to myself, well, I don't want to rewrite that. So I want the variable of integration to be x. So I'm going to take vertical slices. Now, having taken vertical slices, those are either going to be parallel or perpendicular to the axis of rotation. And then, if they're parallel, use shell. If they're perpendicular, use washer. So yeah, what motivates my choice is actually the form of the data that you've been given. More so than, whether I think one of the methods is better or not. Of course, it might end up being the case that if you use the washer method, for instance, you end up with an integral which is impossible. And if the question is asking you to evaluate the integral, well, then you've probably done something wrong, or you need to use the other method. But the general rule of thumb is I want to avoid rewriting the data. So I choose whichever method allows me to do that. But then again, on most of the questions you'll look at, they're going to straight up tell you which method to use anyway, so it's kind of a moot point. Okay, so that's all for now.